Hello everyone, welcome again. I'm continue offline education by using the software. Actually, I'm think I want to continue like this strategy. Also, I'm opened some forum on your system, LMS system, and I'm looking for your comments, but up to now I didn't find any useful comments to change my strategy. I hope you're happy about this situation, and I hope you are understanding my teaching style, understanding from my teaching style. Up to now, we finished chapter 11 and chapter by online. Now I want to continue with the chapter 12, deflection of beam. By the way, I forgot that, and I will announce about the midterm exam date and to style of the midterm exam soon. Let me few days to decide about the exam style. After decision of the exam style, I will announce to name, time, and style of the midterm exam. Okay, let's start with the deflection of beams. Maybe some of you realize that the original slides in Hibbeler's book, the name of the chapter is the deflection of beam and shafts. Mostly I focus on the deflection of the beams. You remember the previous chapter I discussed only to design of the beams. Now I want to continue again on beams because the beam is mostly related to civil engineering structures. Shaft is mostly related to mechanical engineering structures. Therefore, I want to solve just only the beams example. Therefore, I want to do deflection of beams only. Okay, let's start. First of all, what is it, the deflection of beams? And first of all, remember from the chapter 4, we can find the displacement delta when according to axial load. You remember the P load in relation between the delta and P is PL over EA. Also, we know in chapter 5, when our structure has a pure torsion, like the value is 2, and angle change, phi angle change, can be represented as a TL divided by G times G. But we don't know what is the deflection, or so shape of the beam when you apply the force. That you remember that when you this kind of force, mostly in two effects occurred. First one is the moment, the second one the shear force. What is the slope and deflection due to this bending moment or due to this force. So we are trying to find this relationship. So before starting to this relationship, I want to discuss with the new term is the elastic curve. The elastic curve is the line, you can see also blue line in the screen, is the line passed through the centroid of the deformed body's cross section. So you know this body in beam have a three-dimensional system. If we think about the line that passed through the centroid of the deformed body, we can obtain like some kind of curve. This curve we define as this curve as elastic curve. Also, there is some kind of function of the elastic curve. In this section, we are trying to find these formula of the elastic curve. So maybe some of you think that, Hocam, this is you're thinking about the curve, but these definitions is the elastic. Why is elastic? is related to our assumption. Elastic because we thought that our material behave like an elastic material. You remember the Hooke law is the sigma is equal to E times epsilon. That's meaning that the relationship between the stress and strain is elastic. So we assume that in order to obtain the elastic curve as our material is elastic. The second assumption is the small deflection theory. Also, where we are thinking that geometric linear term is that small deflection theory, that is a deflection if we compare with the length of the beam, and deflection of the beam is relatively small than the length of the beam. So why we are using that, you will learn the next slide. You will understand what is the meaning of small deflection. Also, we neglected axial force effect. So if we consider the axial force effect, you remember that if we put the axial load in our beam, our cross section also can change, can vary. Also, we neglect the effect of the axial force to define the elastic curve. Just only we are focusing on the bending moment and shear force. So what is the relationship between the elastic curve function and bending and moment diagrams? So you already know how we can we can draw the moment and shear force diagram in the static course. Now we are passing to finding the elastic curve. So from the high school, you remember that the radius of the curve in calculus, I'm sorry, not high school, I mean the calculus, 1 over rho is equal to y double prime divided by, in parentheses, 1 plus y prime square in parentheses the power 3 over 2. So most of you familiar with, I hope, but if you're not familiar with this formulation, you have two choices. You can memorize or you can learn. Also, you are wondering that, hocam, how you can obtain this relationship? You can click to link given below in C proof, and you can learn how you can obtain this relationship. And I say that in small deflection case, we cannot eliminate the y prime because that's equal to slope of the function. That is, if we say the y prime is equal to 0, we assume that this curve is not curve, it looks like a line. We don't assume, but we can assume that y prime square is relatively slow, that we can eliminate this term, and therefore to bottom side of our function becomes 1. Therefore 1 over rho it's equal to y double prime. In other words, second order derivative of the y with respect to x. So also I want to derive the rho, radius of the curvature by using the flexure formula. Most of you from the high school, I think, like this. For example, if we have a circle like this, if we say about the circle of the radius, we call this a rho, and this angle is theta. If we want to measure to this length of curve, is equal to r times theta. Also theta given is radian degree, radian. Okay, we can, maybe you remember from the high school. If you don't remember, you can learn it. You learn right now. And also I want to raise, where is it? Yes, here we go. So and where is it? Yeah. So if we measure undeformed shape is like this. If we measure to length of the central natural axis, you remember from the chapter 4 this length is the epsilon is 0 on natural axis, therefore the length of on the natural axis is dx. Therefore, if we want to dx with respect to the rho and theta, small angle changes theta, ds is equal to dx is equal to rho times d theta. Here is d theta times rho, length of this curve. Also, I wanted to measure any point. It's like this. I want it looks like y is length of these. It's drawing the green in delta s prime. Delta s prime is equal to the measurement is rho minus y. Therefore, rho minus y times delta theta times angle. So, if I want to measure the strain, you remember the strain is length changed by with the initial length. Therefore, if I write the formulation like this, and if I want to do this relationship to this formulation, I obtain that to it's epsilon equal to y divided by rho. So also we know the stress is equal to modulus of elasticity times epsilon. Therefore, stress is equal to E times y divided by rho. So bending stress, you remember from chapter 4, sigma is equal to, in that line is m divided by I times y. So equation 2 and 3 should be equal. If it is equal, then 1 over rho, and y is disappear, and I wanted to move to E in the other side. 1 over rho is equal to m times ei. Also, you remember the previous slide. 1 over rho is d square y divided by dx square is equal to mx divided by ei. So you remember y is the elastic curve function, the moment. So we obtain relationship between the y and mx. So from the statics, you remember that dmx over dx. So if we take a derivative with respect to x, when we take the moment with respect to the derivative with respect to x, we obtain the shear force Vx. So if we write this relationship to upper function, we obtain that shear force is ei times third order derivative of the elastic curve function. Also, one more derivative, if we take one more derivative with respect to x, we obtain the loading function omega x is also, sorry that I forgot to write, the fourth order derivation of y with respect to s. This is written in here 3, but it should be 4. So if we think reverse, so Vx is integral of the omega x. After taking integral, you remember that we have a kind of the integral constant cy. If we want more integration, mx is equal to integral of the Vx, one more integral constant included in C2. So we have two integral constants, C1 and C2. If we continue, one more integration of the moment, and if we divide it by ei constant, we obtain the slope is dy over dx is equal to also one more integration constant C3 in here, and one more integration, the last integration, we have 4 integral constants. And this is how we can find the relationship between the Yx and loading. Also, if we have in statically determined structures, we can generate is the moment function. Also, we don't need to start with the omega. We can start with the moment for when we are solving question. Okay, so I say that in statically determined plane we can find the moment formula, so we can start with the mx. Therefore, we don't need to start with the omega x, just only we have make a 2 integral. Also, we have 2 integral constant. So how we can find the integral constant? By using the boundary conditions. What is the boundary conditions? Boundary conditions comes from the support reactions or the spatial compatibility conditions. For example, if you have a fixed support, and in fixed support and deflection is equal to 0, also slope is equal to 0. If we include it in our function, Yx is equal to 0, dy over dx is equal to 0. Pin or roller support is the deflection and moment is equal to 0. Therefore, we can write the yx equal to 0, d square y over dx square is equal to 0. If we have a free end, we have two terms is equal to 0. First term is the moment, the second order derivative of the y with respect to x. Second, also shear force is equal to 0. It's also mathematical representations of functions we can represent like this. Also, if we're talking about the compatibility equations, for example, the life of kind of beam, if we can think about, you can see the moment function is not continuous. We can generate two type y functions by using this. Don't forget this. When we are although our moment function is not continuous, also we can obtain the different y functions, but these y function always should be continuous. That's why we are talking about continuity. For example, on point B, if we look from the left side or right side, it doesn't matter. The slope and deflection of these beams should be equal. So now we can start with find our elastic curve function. The first thing is also deflection formulation. The first method is the integration method. Also, I showed that the integration method. You remember, we start with the moment function. We have take two integration and we have find the integration constant. After finding integration constant, if we put our y function inside of the y function, and we can obtain the general form of the elastic curve function. So it's the best thing that we can start with the example 12.1, and we have a point load at the end of the beam. To point B, we have a fixed support. We are wondering that and slope and deflection formula of the beam given in the figure. So first of all, I want to derive the moment function. I don't want to start with the loading. And when you think in deriving the moment function from statics, I have to take a cross section from anywhere of the beam. Okay. If you want, I can do it for you. It's very simple. Like I want to pass to our webcam. We have a beam like this. We have a point load P. I take a cross section anywhere. Distance between I also origin of the coordinates starting from here. Therefore, and I want to measure that it is x. Like this is I am taking the left. This is the point 1, and I take this is 1. This is length is x. This is P. Also internal effects, I call this moment like this direction from statics. So sigma m1 is equal to 0. You can see P times x. I take a counterclockwise is positive. P times x plus m is equal to 0. So I can find moment is equal to minus P times x. So you can see in the screen in moment is equal to minus P times x. So we obtain the moment function. So we can take one more integration. We can one more integration, we get the slope dy over dx in here. Sorry that. Dy over dx, and one more integration if we take, we obtain the equation 2. I'm sorry that I think that you don't see my arrow in here. I want to show the arrow. Yeah. Nope. I want to go back. Where is it? Yep. Yes. One more integration, we obtain the yx formulation. You can see we have two integration constants, c1x plus c2. Now we have a boundary condition. I want to go back to the equation. On point P, we can see fixed support. On fixed support, we have two boundary conditions. You remember that? The first term is y is equal to 0. Then x equal to L. So I can define as YL is equal to 0. The other term is the slope is also equal to 0, dy over dx on L is equal to 0. So I apply the formulation in here, and first of all I want to start with the slope. After starting with slope, I can find the C1 coefficient. Also in second boundary condition, YL is equal to 0. If I put YL equals 0, I can find the C2, and after that if I put C1 and C2 in the equation 1, we can find Yx formulation, Yx function, sorry that. Okay, so also if I take one more integration, I can also find the slope function. I want to start with the example 2. In example 2 we have some kind of two triangular law, but function is not continuous, and from 0 to L over 2 is different. From 0 to L over L over 2 to L, the omega function is different. So also in the question, slope and deflection formula is given in the figure, and find the maximum deflection. You can easily realize that maximum deflection occur at the middle of the beam. So also you can see on the slope at the middle of the beam is 0. So we can easily see, and dy over dx L over 2 is equal to 0. How we can define this? Because the system looks like symmetric at the middle of the beam, and the y is the maximum. You remember from the high school, when any function is maximum, so one more derivative of that function should be equal to 0. So I want to, how we can say I solve, moment function is not continuous, so I have to divide the two functions, but you know but system is symmetric, so if I solve any function from left side or right side, doesn't matter, we can easily find the general elastic curve function. I want to choose the left one, that means the y1x, which is started from the x is equal to x start from x, the boundary of the x is 0 to L over 2. So how we can start? First of all, I want to derive to do loading function. What is the loading function? Loading function is omega is equal to 2 omega 0 L times x. If you have any trouble to find, okay, I can help you. So I want to pass to the webcam. You remember when the x equal to 0, omega is equal to 0. So when the x equal to L over 2, is omega is equal to omega 0, 0. So slope m is equal to omega 0, this is the L over 2, just L over 2, therefore, and slope is equal to 2 omega 0 divided by L. The function you can see started from the x equal to 0, therefore this function omega x is equal to slope times x, therefore this is equal to 2 omega 0 over Lx, from simple mathematics style. Okay, I want to go back to our slideshow. You can see our omega is equal to 2 omega 0 function. If I want to derive to the moment. Now I want going to do again doing this from statics. You remember that we can find the support reaction. This system is the symmetric, therefore we can easily find the support reaction, because that's equal to total load divided by 2. After finding the support reactions, we can take anywhere of the beam and we can find the moment function, and the moment function is equal to omega 0 x cubed divided by 3l divided by 0 over omega 0 L divided by 4x. One more integration, we can find the C1 coefficient, and one more integration of this, and we can obtain the elastic curve function. We have two integrational constants. Now we will start with applying the boundary conditions. The first boundary conditions, you remember, and we can realize that in first this and this and is the roller support. Therefore, on roller support we can say y is directly equals to 0. Therefore, I have to write y0 equal to 0. If I put this load, you can this term, and this term is equal to 0. Therefore, C2 is equal to 0. So most of you think that hocam also xl is equal to also yl is equal to 0. It's second boundary condition, maybe you can say, but unfortunately I cannot say because I am solving from x is equal to starting from the 0 xl over 2. Therefore, I cannot work with this part, the right part. Just I am only focusing on the left part. So I have to find the additional boundary condition on right part. What is the x additional boundary condition? Also, you remember when we are defining the boundary, the maximum y max is equal to middle of the beam. Therefore, I can say to slope on the beam on point x equal to L over 2 should be equal to 0. Therefore, I have to write the slope function, and I have to write instead of x instead of L over 2 for x in the function. I can obtain the C1 is like that function, so I can find the yx, and also I said the y max is equal to at the middle of the beam. If I put L over 2 instead of x, I obtain that the y max is equal to 1 over ei minus omega 0 L over 4 divided by 120. Maybe some of you think that I am passing so fast, but most of calculations is related to mathematics. The theory is not complicated, therefore I am passing a little bit fast. But if you have any question, okay, please let me know, and we can write on forum and we can discuss, and I can also solve the questions in detail. Okay, now I want to pass to the third question. You can see the beam is subjected to distributed load. Again, the load function is not is a continuous function. We can find the elastic curve function, and also we are the vertical reaction on A. Also wondering that, and AI is constant. So you can think you can easily find, but if you look in detail, is the and on point A we have a roller support. We have one reaction in here. Also point B is the fixed support, and 3 reactions in here. Therefore, our total reaction is 4. In other words, our systems is not statically determined. It's statically indeterminate system. Therefore, we cannot unfortunately easily obtain with the moment function. So how we can do? So I said we have only one more term is needed to find the moment function. Therefore, in first order statically indeterminate system, therefore I can say, like, I can assume ay as an unknown. Okay, I try to generate the moment function with respect to ay. Okay, then I can pass to do yx function by taking 2 times derivative. So I have how many unknowns? C1 I don't know, C2 I don't know 2, also third term is ay. So I need 3 boundary conditions in order to drive. If I have or not, let me check. You remember that on point A, y is equal to 0. The deflection equal to 0. Also point B, deflection equal to 0 and slope equal to 0. Therefore, how many functions we have? We have 3 boundary conditions. Therefore, we can find all unknowns by using, if we applied boundary conditions. First of all, I want to start with the easiest one. Y0 is equal to 0. This term, and this term is disappear. Therefore, C2 is disappear. So this term we don't need to consider because C2 is equal to 0. You remember that the second one, slope is equal to 0 on point B. Therefore, I write dy dx on point x equal to L is equal to 0. I put this function L instead of x, and this term should be is equal to 0. If I put CL on, C1 is equal to, not clearly because it's later, this depends on AY2, and I remember there's a 1, equation 1. I want to continue, and also we know the deflection is equal to 0 on point B. Therefore, I write to L instead of x, and I equalize with the 0. And then we have 2 functions in here. Also, I want to write this term instead of C1. Okay. Now, just only one term is remaining in this equation. Therefore, I can easily find the AY. AY is equal to omega 0 L over 10. And if I substitute this AY to the C5 function, also I can find the C1 is a minus 0 or 0 omega 0 L cubed 120. If I substitute AY and C1 instead of the YX function, I can find our elastic curve function. And if I have it, okay. Now we are starting with the discontinuous functions. Maybe you can realize that also in second example, if our function is not continuous, especially the moment function, we have to divide our structures in sub-member. Also, we have to discuss with the not only one y function, elastic curve function, more than one functions we have to focus on. Therefore, in solving, time takes too much time if we apply with integration method. So for integration method is convenient, this moment is a continuous function, but moment is not is a continuous function. We have to find the alternative. Also in these cases, Macaulay functions can help. So I want to say the Macaulay function is the approximate function. Macaulay functions, how we can apply this? Macaulay function, the approximate way to convert the discontinuous function to continuous. How we can show is that expression is like some kind of the brackets, but not like the curved one is like this brackets, and is x minus a times a. N is the power of the functions. A is equal to locations of the external force. So also we have some kind of rules. Is the value of the Macaulay function is 0 where the location whose internal effects is calculated is lower than the lower function. In other words, if you have to calculate the deflection on anywhere is point like location x. If the x is smaller than a, your Macaulay function is directly is 0. We cannot put any negative value. If I put 2, if it's equal to x greater than a, we can write as x minus I power n. So these brackets showing like these definitions of these functions represented as like this. Also, if I need to write to the Macaulay functions, our distributed load should continue at the end of the beam. So if if I have any distributed load which does not continue at the end of the beam, we have to convert to our deflection function. If you have to convert to this distributed load type, if we can't distribute it, we cannot apply the Macaulay function. Also, some kind of the singularity cases, So what does it mean? For example, in here, when they execute a, this we can obtain 1 over 0. It's going to the infinity. This is called the singularity. In order to, but for in singularity case, we are using directly is the equal to p. What does it mean? P is a function of value equals the content of the parameter, this function. So p times equal, this term is becomes 1. Therefore, this value is equal to 1. So, also, don't forget to do not combine for, do not open these parentheses. When the parentheses terms is different. For example, if we have a x minus 5, also if we have a x minus 2, we don't open and don't combine. We can always solve these values separately, okay? It is extremely important. If we combine, we can make a mistake. This is the table of the Macaulay functions. Also, when we are solving equations, solving Macaulay functions, we have to apply these tables. So you can see every detail available in these Macaulay functions. Now I want to start with the example 12.4. In example 12.4, this kind of beam, and it's 8 kilonewtons start applied on the point C, and also one more to moment 120 kilonewton times meter applied on point B, and we are taking that for determine the maximum deflection of beam shown in figure using Macaulay function. Also we take to EI is constant. So let's start with 2. So maybe most of you think that we have just only 2 forces. Unfortunately, we have not only 2 forces, because also we have to find the support reactions on point A and B. First of all, we are starting from the statics. We can find the support reactions. We can easily find the support reactions. Is point A is equal to 6 kilonewton and point B is 2 kilonewton. Okay, so we have how many forces? We have 1, 2, 3 forces, 1 moment. We have 4 moments. So by looking to our tables, by using these tables, I can just value is minus 8. Why is the minus 8? Because the positive direction is upward, therefore as this direction is downward, therefore minus x. This second and third forces is the upward direction, therefore the value is 6. Distance from the start is the initial point on location of this 8 kilonewton is origin of our coordinate. Therefore I put A is equal to 0, but point 6 point B, sorry, I don't know, where is the light of ABC? Yeah, by point A, this is the A is equal to 10 and 2 kilonewton, and point A is equal to 2. Also in moment, the value is the counterclockwise. Clockwise direction is positive, but this moment also clockwise direction, therefore the value is the 120. So also I put I find the A values. Also these the values is 30, but also I want to say the extremely important term. These force and these force we don't need to include in our functions, because you can see to A is 30. So x, all values of x always is equal to or lower than to 0. Therefore all times is Macaulay functions of these form values obtained from these forces is equal to 0. Therefore we don't need to put these values. But if you think, if you confuse, I am confused, I want to put, you can put, it doesn't matter, but we don't need to put, because all x values, these terms always 0. So I eliminate, therefore I have 2 force in force 1 and force 2. I write the moment function by using this table. For example, I have 2 forces, that is formulation is P times, in parentheses, x minus a to power 1, therefore in turn minus 8, I write to put P, x minus 0 to power 1, 6 times x minus 10, I write in power 1. One more integration, I obtain this, and power is greater than 1 and divided by this 2. Also increase 1 by divided by 2. C1 coefficient appear. So one more integration I obtain. I have two integration constants, C1 and C02. I have to apply the boundary condition. We have two boundary conditions. We have one roller and one pin support and one roller support. When the x equal to 0, y is equal to 0. When the x equal to 30, y is equal to 0, I apply these boundary conditions. And I have two functions which depend related to C1 and C2. Two functions, two unknowns. We can using to any rules. We can easily find C1 and C2. I will include it in the function and general function, and I obtain two elastic curve function. Okay. Also, I want to continue. They are talking about what is the value of the y-x is the maximum. So, and y max is the location of x where is the equal to max. There you have two conditions. First condition, maybe you can remember from the previous example, derivative of the y is equal to 0. The second one also we have to check two end locations, x is equal to 0 and x equal to L, and we compare these 2 points. Which one is the greater we will choose, and we will choose that point. So I first of all I start with the first point. I want to take the derivative slope, and when you take the slope in equalities, so for minus 4 x is 0 power 3 2, and I want to convert to the polynomial function, and after in second order polynomial function I can easily find the x. Okay, now in here maybe I warn that don't open the parentheses, but I have to open the parentheses because in order to find x I have to open the parentheses. Okay, therefore what I have to also check is these terms should be greater than the 10 and 0. You can see this term is greater than 10 and 0, therefore this value is okay, correct and acceptable. After apply to 20.3 in the equation, I can obtain this displacement 5006. Now I want to compare with two end locations. You can see y30 is equal to 0 because there is a boundary condition, roller support in here. Therefore 30 is equal to 0. But initial point, is there any displacement available? Also I want to put to 0. I am wondering that when you put to 0, this term is equal to 0, this term is equal to 0, this term is equal to 0, then there is the y value exactly equal to minus 12,000 divided by EI. It's also, if you compare two terms, which one is the greater? I think that the second term is greater, therefore y max is equal to y0, this equal to minus 12,000 divided by EI. Also we are running that hocam v1 is the minus is lower than the positive value. I am talking about the absolute displacement, I am not talking about the minus and positive terms. We are always talking about the absolute displacement. Last questions about the Macaulay function. Also we have some kind of the loading type, and point A is the fixed support, point C is the free end. We have one distributed, one moment, and one point load. But it's our distributed line is not continue at the end of the beam. Therefore, we need to change the strategy. I want to solve these questions on webcam. Okay, how is it? How I can solve? Let me control my notes in here. Okay. Anyway, yeah. So if you look at the Macaulay function, I want to go back to the screen. all the Macaulay functions, you can see the distributed load should continue at the end of the beam. Therefore, in the question, maybe I want to go back to the webcam. If our loading like this, but this loading is not acceptable, I want to convert this beam like this. This is equal to this times and this is 8, this is 8. If we combine these, we can obtain we can easily convert to our initial distributed load. Now these true distributed load can be represented as a Macaulay functions. Also, I have put the additional forces. I have, you remember, 50 available in here, also 12 available in here. So I need to also find two moment reaction forces on point A. You can, and I want to write like AY and moment A. You remember the AY is equal to 8 times 50. How we can obtain this? Look at the I want to go back to the, let me check. Yeah, you know, 8 times 5, it's 8 times 5 is coming from here. Okay, then plus 12. Where is it come from? This force is any vertical force? Not, I don't think so. Therefore, AY is equal to summation of this. This is equal to 82. How we can obtain the moment A? Moment A is equal to, let's see, after from statics, I want to go a little bit fast. Therefore, sorry that. So you can see, and 8 times 5 is, I say, the 40. Like here, this is 40 in here. This value is 2.5. Also, this location is 9. If I take moment to the A, I can obtain MI is equal to 40 times 2.5 plus 50 times 12 times 9 is equal to 258 kilonewton times meter. So I want to include our function. This is 52. This is like that, 258. Now I can use the Macaulay function formulation. I have how many type of force? I have 1, 2, 3 distributed, 4 distributed, 5 and 6. But you remember that I don't need to use the 6th one because its location of the load is at the end of the beam. Therefore, I don't need to count. Therefore, I don't write. Just only I write like these remaining 5 forces. Okay. First one is the moment. I don't want to go back on the table. You can check with the tables. Okay. Therefore, I don't. Just only I write the value and location, and is the name, value and location terms. The name is the moment A. Value is, I write the counterclockwise, therefore I have to write the minus, and value is minus 258. Location is the initial point, therefore A is equal to 0. In on second one is I want to write the AY is upward, therefore its value is equal to positive, therefore, and then also location is equal to 0. Third one is the moment. I want to write the moment. I want to write symbolize as M0. The value is, you can remember, the 50 is the clockwise direction, therefore I write the positive 50. Location is 5. The fourth one is the I want to write the first distributed load. Its the value is the distributed one. I symbolize this. The value is the minus 8 because there is locate in downward direction. Also location is 0. The fifth, the last one, is the omega 2. Also value is the positive 8 because the direction is upward, and location is starting a here from here, therefore this value is, this length is 5, therefore I have to write 5. Okay, so I want to write moments by using these four relations. So by using the Macaulay function table, I don't want to go back and look at it. I think I can go and look at it like that. Mx is equal to, and I want to go back to the table. I give up. I change my decision. Where is yeah, here we go. Okay. Yes. So moment. First term is moment. Moment is equal to m0 x minus 8 power 0. Therefore minus 258. I don't want to x minus 0, just only I want the x. Where is the power? Power is, I'm sorry, I want to go back to both. Yep, its power is 0. Then I want to, in second term is the ay is the force in upward. You remember that p multiplied by x minus 8 power 1. P is equal to force is equal to 52. Its length is equal to 0, therefore I don't need to want to minus 0 like x, and power is 1. The third term is the m01. You remember m01 is also moment. I have to write this formulation, and values of positive 50. X minus location is 5, therefore I have to write 5 in here. Power 0. The fourth one is the distributed load. Distributed load is in here, omega 0 over 2. Therefore I have to write to 8, you remember, and location minus 8, therefore I have to write minus 4, and x to power 2. The last one is the positive 4. You can see x minus 5 power 2. Okay, so we have the moment function. If I one more integration, we can obtain the slope function. So one more integration, we apply dy divided by dx, x 1 over ei. If I take one more integration, you can, these terms 0 becomes a 1, therefore I have 258 x to power 1 plus 26 x power 2 plus 50 x minus 5 power 1 plus 4 over 3 x 3 and 4 over 3 x minus 5 to power 3. So one more integration, yx 1 over ei minus divided by 2 129 x to power 2. I'm sorry, in order to gain space I don't want to write this parentheses, sorry that. Also this is also 26 divided by 3 x to power 3 plus 25 x minus 5 to power 2. I want to use the small space in bottom, sorry that, for bad writing. If I am using this one, minus 1 over 3 x to power 4 1 plus 1 over 3 x minus 5 to power 4. It's very complicated function, you can see. Don't worry that. Also I have two boundary conditions. I want to delete this part, sorry that I don't have enough space, but you can see when you reword our stream. So you have two boundary conditions. You remember that fixed support in initial, therefore y0 is equal to 0, displacement is equal to 0, dy over dx is equal to 0. From here we obtain C2 is equal to 0. From here C1 is equal to 0. Therefore, I'm sorry, and here I forgot to write the C1 and C2 coefficients. Also I don't need to write, because also this I obtained that this term is equal to 0, therefore I don't need to write. In general formulation of the functions becomes this. So it's long calculations, I know, but theory is extremely simple. Maybe you can realize that. Do not start too long computations, okay? Just only focus on the theory. Okay, you know, in the exam you have to do some calculations, but you know, if you know the theory is very well, okay, you don't have any trouble to obtain get correct results. Also I can promise that don't talk about the miscalculations. In my opinion, I can promise that I don't need to lose much more points. You don't lose much points if you make any numerical mistakes, numerical errors. Another way to obtain slope and deflection of the beam, to obtain the deflection of the beam, is the moment area method. And in momentary method a little bit more simple than the other methods, especially in calculations. If you want to obtain two numerical solutions, I prefer to use the moment area method. In the moment area method we have two theorems, and first theorem is if we obtain the moment diagram like this, and if we divide it by EI, and we are wondering if we take an integral between from point A to B, the result of this integration is also it's equal to area of the curve from point A to B. It's equal to slope change between the A and B. In other words, if we say the slope is theta, if we represent as a theta B minus theta A is equal to is total area under this curve, is moment function divided by EI curve. This the first theorem is this. In second theorem, if we want to, after obtaining two areas, for example, if we want to multiply by x, if we add the integral in this integration m over I x, also it's equal to x dot x prime. What does it mean? The x prime is to centroid of these area between the centroid of the D's area and point B. So the multiplication of this term and area of the D's, the total area, it's equal to vertical deflection change. In other words, if you know vyb minus ya is equal to this term. If our moment functions, it's easy to it's very simple. For example, triangle or circle, or I don't know, the rectangular shape. So we can easily find the centroid of these areas. Additionally, also we can also find the total area. Therefore, we can easily find the moment and slope changes. Therefore, moment area is very useful. But if our function is a little bit complicated, okay, I don't prefer to use the moment area method. Okay, and its a good application is example 12.6. It's first of all in 12.6. They are wondering that slope of the beam on the figure and at point B by using this formulation. Again, there is no numerical values obtained. We are finding that with respect to P, with respect to L, and with respect to EI. Okay, so try to remember I want to go back to the theorems. The first theorem, you can see they're asking the slope change, and difference between the slope change is the integral of the moment divided by EI. So we have to start with the moment diagram. Its moment diagram is very simple in this, like this beam, and by using your memories from statics, and I want to draw a little bit fast, so disturbing this. Maybe most of you remember how we can draw this line. Okay, moment diagram should be triangle. It's starting 0 in point B. On point A, this is the maximum. What is the value in this point? It's P times this distance. Therefore, this is equal to P times L. But you know the moment is negative in the statics. Therefore, I have to write the minus PL. And if anyone have a trouble to how we can obtain that moment diagram, you can let me know, and I want to tell you in detail, but it is not complicated. Definitely I can say. So now I have passed the moment area method, so I am obtaining, this is the moment diagram to a moment diagram like this, mx. So how we can say, just this is our diagram. So they are wanting the slope change. So they are from here, we call this point A, point B. So if the theta B minus theta A is equal to its area of this triangle. What is the area of this triangle? This length is minus PL, and this length is to be called as L, therefore multiply by L divided by 2. This is equal to minus P L square over 2. I forgot that this is, I am wondering that I have to divide it by EI in order to use the moment area method. You know, our diagram should be M over EI diagram. Therefore, don't forget to divide it by EI. Therefore, PL square 2EI our result. Just that. This is, sorry, not the result. This is difference between the theta B minus theta A. The question asks that to what is the slope on point B. So first of all, we have to find 2 in this formulation. We don't know the theta A, slope A. What is the slope A? Slope meaning that first order derivative y with respect to x. So you remember, in point A is the fixed support. Therefore, and slope on fixed support is equal to 0. Therefore, theta A is equal to 0. Therefore, this term becomes 0. Therefore, this term directly equal to theta B. Therefore, this value is equal to theta B is equal to minus PL square over 2EI. If you look at the book results, you can find a different result. I think that they're asking at the middle of the beam like this P, but they made a mistakes. Definitely to P minus PL square 2EI is the correct answer. Okay, the next question is the example 12.13, but I think we forgot to put the shape in here. Let me 5 seconds. I think I can easily find this. Before using shape, I cannot find. I have to go back to do Google Drive. Let me 5 seconds to find the shape. Also, you can find to our previous slides, previous lecture notes. And where is it? Let me 5 seconds. And also I can say the here we go. Which question I want to say like this, not shaft design. Like where is it? This is not chapter 11, sorry. Chapter 12. Yeah. This is chapter 12. Where is it? Not this one, this one. Yeah, this shape. I want to use this shape. I want to like copy. I minimize and I paste. Now our question is ready. I want to continue. Okay, determine the displacements from B and C, the beam shown in the figure, by using the moment area method. Also, there is no numerical values given in this question. Therefore, I have to find values with respect to moments, L and EI terms. So, what is the moment of these beam? And it's easy. I want to use the, sorry, did you see or not? Sorry, this is the question. Okay, and I want to draw the shape like this. And this is the moment in here. In order to get to moment diagram, I want to take a cross section anywhere of the beam. So I want to define this X. This is the RM0. This is the internal moment, in direction internal moment like this. Okay. So I want to define this point as a 1. Sigma M1 I want to take the counterclockwise is equal to total moment is 0. Therefore, I want to say this to mem X is equal to directly minus M0. Therefore, our moment function, if I want to derive the moment function in this figure like this, it's the constant and this value is equal to omega 0. This is the 0. So if I want to convert to the moment area method, I have to think like minus M0, I have to divide by EI, therefore is moment function like this. This is the point A, this is the B, and this is the C. So I have to calculate with the area. So first of all, I want to start with the point B. Therefore, I want to talk about the area A1. As area A1 is equal to area A1 is equal to minus M0 EI, this length. Also, this length is the L over 2. Therefore area A1 is equal to minus omega 0 L E I. So, and I want to use, I don't need this space anymore, therefore I want it like this. So I obtain so they are wondering that I want to go back to the question, determine the displacement from the points B. So you remember we have to use the second theorem. What is the second theorem? It's the YB minus YA is equal to area times X bar. So what is the area? It's I already calculate in here, M0 times L over EI, the minus term in here. I'm sorry, I forgot to L over 2 like this. Okay, sorry, it's the length is L over 2. So times X bar. What is the X bar? X bar is the centroid of the area between the center of the area and point B. This is the centroid of area, is the middle of the length. Therefore this length is equal to L over 4. Therefore I have to write L over 4. So this multiplication of these two terms I obtain minus M0 L square 8EI, and this value is equal to YB minus YA. So you remember, I want to show point A is the fixed support. On fixed support you can remember that the deflection is 0. Therefore YA is 0. So this value directly equal to YB. Okay, it's very simple, you can see. Now I want to pass to the second question, YC value. In order to use the YC value, I have two strategies, because I have already know the deflection of the YB. Also I have already know the deflection of on point A. Any point we can check as a reference. I want to use the reference point and again point A. Therefore from point A to C, my formulation is YC minus YA. Therefore I am wondering that to this whole diagram, the rectangular shape, what is the area of this? You can remember that this is the minus M0 divided by EI. Total length is L. Therefore the area is equal to minus omega divided by EI times L. So if I want to go back to formulation, area times X bar. So what is the X bar? X bar is centered of this rectangle. This length is X bar is equal to L over 2. So I have to write to minus omega 0 EI times L over 2. Therefore this equal to omega 0 L squared to EI. Don't forget to write the minus. So you can remember that YA is equal to 0. Therefore YC is equal to directly the minus M0 L squared over 2EI. Sorry. And you can see the results in here. Okay, the last chapter, subchapter of the chapter 12 is the, I'm sorry, I want to show the results on slideshow, and if you look at the solution you can see the exact results by hand results. Okay, now we are talking about the method of superposition. superposition is like to, how I can say, as you can easily understand when I read the definition. If our necessary conditions is loading is linearly related with the omega x, therefore the load is linear. Also I can say our material is linear. Also we assume that the small deflection theory, we can apply the method of superposition. Superposition is meaning that we can, it is possible to, in order to find the slower displacement or any internal effects such as moment and shear force, it doesn't matter, we can divide by the effects, for example external forces, and calculate separately. And if we add the summation resultant values, okay, the resultant value exactly equal to the how we can say total effects when we get the results. I think that my definition is not easy to tell. Okay, I think I can easily show in this figure. Okay, for example, if we have a like this force, you know, this is the statically indeterminate system because the point A is the fixed support, point B is the roller support. The number of unknowns is 4. So we don't know how we can calculate the reaction forces by the statically. So, but we can use the method of superposition. We know on point B, the deflection is equal to 0. So I want to convert this system like two different kind of beam. So you can see in first beam, I eliminate the reaction forces, the B. And when you eliminate reaction forces, this system looks like a cantilever beam. And by using this point force, I can calculate the deflection on point B. Also, I want to additional system and point like on point B. Also remember that we have a reaction forces on point B. I want to put By instead of B, so we don't know Bi, by using deflection by respect to the By. So if we combine these two design and the modeling, we can obtain the whole system. So if we resultant deflection of this system should be the resultant deflection of the point B. In other words, we know the point B, deflection of point B is equal to 0, therefore the summation of these deflection should be equal to 0. By using this relationship, we can easily find to do reaction force on point B. I think if I solve a question, you can easily understand. This is very similar question to previous shape. In example 12.8, this is the last example. If our beam subjected concentrated force on point like this, we can call it as a C, determine the reactions and support. So we can, I say, and we can use this method of superposition in here. How we can doing this? I can use both web and camera, and this method of superposition is like this in here. Normally, if I want to do free body diagram, in here I have AY like moment. Also, I eliminate the horizontal force because AX is equal to 0, therefore I don't want to write the A. This is the BY, like B. Okay, this is B. So we have 1, 2, 3 unknown, but we can apply just only 2 equations, therefore we cannot easily find. This is the whole free body diagram. This is whole system. I want to equalize like this. First of all, I eliminate the By, so M, AY, and P. So we can, by using this load, we can find, how is this like shape? Like this. Okay. we can easily measure the deflection on point B, YB 1. Okay, because this is the statically determined system. Also, this first model, also one more model I want to use, therefore which term is B and P. Also I want to do moment AY. Also I have to relate it to B, and I want to add the P, I want to add the BY and P. So I want to like the MY, IY like this. This term is not exactly same, therefore I have to write the 1, M2, E2, just okay. And summation of this system is equal to, by using loading like this. So also, I'm sorry, I forgot to delete this P like this. Okay. So if I want to measure vertical displacements on point B, okay, YB2, YB1 plus YB2 is equal to 0. Therefore, by using this, I can easily find the BY value. Don't stuck like these subtractions. I don't want to discuss the value of this. Just only I want to concentrate with these deflection. How we can find the deflection? I can do the easiest one, the moment area method. I want to start with the first model, and I want to delete all parts. Okay. And in first model, I have beam like this. I have point load. So you remember this total length is 2L. You can remember. If I want to draw the moment diagram, you can remember I have a triangular shape, that this term is the P times 2L, therefore I have write like minus in here, therefore this should be minus. Okay, so this is the point B in here. So I am wondering that to point B. So in moment area method, I need to calculate how we can calculate point B. So in moment area method, so if I reference point A, so I have already know Vy equal to 0. Therefore, because the point A, we have fixed support. So VB minus VA is equal to directly Vy. It's equal to, and area of this shape times to center of this shape to point B. So we have two area, and so this is equal to, this is the midpoint, therefore it's to this is minus PL. Okay, A1 and A2, A1 times x bar 1 plus A2 x bar 2. This is the x bar 1, this is the x bar 2. So A1 is equal to, don't forget to divide it by EI, 1 over EI times, I want to put the parentheses, A1 is equal to, this length is, I remember that, the L, and minus PL times L, area 1. X bar is the half of 2L, therefore I have to write L over 2. Okay, now I want to pass to the second area. Second area is also, this term is the minus PL, therefore I delete this like minus PL times L divided by 2, because I have a triangular shape. Also distance is 2L over 3. So if I sum as these terms, 1 over EI minus PL cube over 2 minus PL cube 2PL cube divided by 6. If I combine this, I have to multiply by 3, and this is equal to minus 5 PL cube divided by 6EI. So what is this value? This was exactly YB1. Okay, so this loading condition, I obtain YB5 minus 5 PL cube 6EI. Now I save this value. Okay, and I want to pass to the second case. In second case, in second model, we have model loading like this. We have like B in here, there is no P value in here. I want to write like the BY. So if I want to draw a moment diagram like this, this is equal to B my times L. This is the negative, therefore, oh sorry, this is the positive. Sorry, my moment diagram is wrong. And this is the positive. BY times L. Okay. Don't forget to divide it by EI in order to use the momentary method. This length is L. Therefore, YB2 is equal to, you remember that, YA is equal to 0. This is the X bar is equal to 2L divided by 3. YB2 is equal to area times X bar. The area is BY times L divided by EI, L over 2. 2 meaning comes from the triangle, shape of triangle, times X bar, you can remember that, 2L3. Therefore, and YB2 is equal to BY times 2L cube, oh sorry, 2 is disappear, you can see, L cube over 3, if I made any mistakes. So you remember that YB1 plus YB2 is equal to 0. I can remember that YB1 is the minus 5 PL cube divided by 6EI plus BYL cube, sorry, 3EI, I forgot this, 3EI is equal to 0. I can see L cube is disappear, 6 is disappear. I'm thinking that this term is going back to the right side. Also this disappear, this 2. I can see BY is equal to 2.5p. After these calculations, now I can find two reaction on BY. Now our systems convert to the statically determined system because I have already know the BY value. So BY is equal to 2.5p. This is the P. So I can easily find two support reaction AY, and I think I can use one is, I think that M, like M should be like this direction, M. So sigma Fy is equal to 0. I can say AY is equal to minus 0.5p. That's, in other words, AY is downward direction. Also sigma moment A is equal to, if I take the counterclockwise, is equal to 0. This is the minus M AY plus 2.5 P times L minus 2PL is equal to 0 and moment is equal to 0.5 PL is direction is clockwise direction. So my assumption is correct, and this is the result. Also, I want, if I have chance, I have to contribute the results. Oh, I didn't write the result. Let me check my hand calculations. Okay, it's correct. So this is the last question of the chapter 12. If you have any question, please let me know. Okay, see you soon. Bye bye.